and thank you for downloading this TODAF podcast.
Of Introduction to Aerospace Engineering. Introduction to Aerospace Engineering 1, because we've distributed it over two parts, in the first period and the second. My name is Jaco Hoekstra. I've seen most of you already last Friday and many of you 2 weeks ago. I'm the dean of this faculty, and it's also my honor to have the tradition of giving you the Introduction to Aerospace Engineering, which I was also taught once by the dean in those days. I also went to college here. I worked at the National Aerospace Laboratory for about 16 years before I came to the faculty. And 2 years ago, we set up a completely new curriculum, which one of the key courses of the first semester is Introduction to Aerospace Engineering. I think we need new batteries or something. Maybe, could you please go to the service desk and ask for new batteries for my microphone, please? So we set up this new course, Introduction to Aerospace Engineering, to give you an overview of aeronautics, of aerospace. So these are the goals of the course: to give you a bit of historical context. We'll use the timeline of the development of aerospace as sort of our storyline. But main goal is to give you the basic knowledge of the principles of aerospace, both technologies, systems, as well as physical principles. Of course, this should also give you the basic understanding of why aircraft look as they look today. And it should give you an overview of the different disciplines that are within aerospace, and in the module AB, the first module, in aeronautics. Because there's, of course, a problem with a course like this, is that it teaches many disciplines. Because we see aerospace as a collection of disciplines. Yes, thanks. I'll change them quickly. Is a bit of a problem, because if I tell you only about aerodynamics, you will get airplanes looking like the center right. Aerodynamics people would like changeable shapes, very fluent, very slim, while the stress group, of course, prefers straight bars which are easy to calculate. And if you ask the power plant, they say the main system is, of course, the engine, if you ask the power plant group. And yes, you need some extra wings. There is actually an aircraft that looks like this. Apparently they had a very powerful engine group. So how do we do this in this lecture? Well, the idea is to start in the center, start with the aircraft itself, basically look at all the disciplines, and that's where the module AB is for. And then later, within the course, you will get different modules on different subdisciplines. And then after the two courses, Introduction to Aerospace Engineering, you will get separate courses on all these different disciplines. So we sort of fan out from the middle. The setup of the course, you have Introduction to Aerospace Engineering 1 and 2. 1 is aeronautics, so you get the introduction to aeronautics, aerodynamics, and some flight dynamics about the performance of aircraft. Then you get an exam in October. And then in the second period, we have the space module that we start off, the overview of space. Then a bit of orbital mechanics, and then also in the second period is the module Materials and Structures, which is identical for space and aeronautics. Well, this is the schedule, hard to read. I'll put it up the blackboard. You will see that you already will have had two courses of Intro to Aerospace Engineering before the Dutch group even starts. But more importantly, also note that in the second week, there are extra hours here, instruction, which for the English group is on Wednesday, split in two, which is an instruction, which will mean you'll get a bit of extra stuff, but mainly exercises which you will do in groups, which we will together try to prepare you better for the exam. So those are extra. You won't have them in the first week, but you'll have them you have them 4 times in total. And there will also be, as an extra to this course, a materials and structures practical scheduled in the same time. This is only the first 4 weeks. These are the other 3 weeks. You will also see that the lecturer changes. So per module, we have different lectures, just 1 or 2 per module. The book, I hope many of you already got the package from the VSV. And otherwise you should, because you need it already tonight. The book, I don't think it's the batteries, but okay. The book of Anderson, they made a new edition this year, 7th edition, but the 6th edition of last year is also fine. So if you got it second hand from somebody, the 6th edition should also be fine. Also mind the Blackboard site. Register for the course. I don't know if Gillian Saunders already told you, but you should register, should enroll for the course, because this gives you access to all the course material. The book is quite thick. As you can see, this is the book. This is 6th edition. This is the hardcover of the 2nd. And the good news is you don't have to study all of it. To know what you need to study, you need to follow the courses. All the material that we treat during the lectures is mandatory for the exam and will be returned in the exam. And we will refer to the relevant chapters as well. And also, at the end of the period, I will put up a note explaining exactly what you need to study for your exam. But in the meanwhile, make sure you get your notes and watch the Blackboard site, because that really shows what you need to learn. We'll also do some stuff today, for instance, that's not in the book of Anderson. And I will give you a handout in the break which contains some information on that, but you'll probably also need your notes. Okay, air transport, aeronautics, indispensable today. Here you can, if you can see it, you need to dim the light a bit perhaps. Here you can see a daily traffic pattern of air traffic. You can also see daylight shifting, so you see within Europe people are waking up right now. And also interesting is to note the pattern over the Atlantic Ocean, for instance. One day, one half of the day, it goes from west to east, and now the ocean becomes empty, and then the direction reverses, flies in the other side, to the other side, and that's also why you always arrive in the early morning here, coming from the States, and you leave somewhere from noon till the afternoon, because they don't have radar coverage over the ocean. You see the States, they have really woken up by this time. A lot of traffic, thousands of aircraft in the air all day, and any given aircraft, a modern airliner, spends more hours in the air than on the ground nowadays. But also, if you look at some numbers that should indicate could indicate the relevance for society. How many passengers do you think travel annually by air? Any idea? Any guess? 6 billion. Nearly the complete population. Well, not everybody can afford it. It's a bit less. It's actually 2.5 billion. 2.5 billion passengers, which is still quite a lot if you consider that only a small part of the world is as developed to actually travel. I thought it was a really high number. As a researcher, we always have to explain also the relevance of our work, and they also would like to know how many jobs do you provide as aeronautics, if we have it. Well, the answer is 15 million jobs, and then we do not count tourism sector because, well, you could say it would be less without aeronautics, without air transport. Also, the numbers of the growth is quite hard. It's an exponential growth of air transport, 5% per year in the past, they said, but it's even expected to, well, if you accumulated it to 145% from 2007, when the study was done, until 2026. And there are, of course, economic crises, like, well, currently we have something going on. This only slows the growth and makes it constant for a little while, and you'll see normally that after 1 or 2 years, it picks up the exponential growth again. Most of the growth doesn't happen in Europe and the United States, but in Asia and South America. It's not just important to move people, but also if you look at the manufactured goods, 1/3 of all the manufactured goods is transported by air. And this is 1/3 is based on the value. And that, of course, is a higher number than if you look at the mass, because high mass, low value is typically done by ships, while high value, low weight is typically done by air. On average, if you look in an aircraft, it's mainly fresh foods or flowers or laptops and tablets and that kind of stuff. Those are typical cargo items that are moved over the air. High-tech systems, fresh goods. Very important, if you work later in an aerospace research department, the lowest number that any effort that the government puts in, any money the government spends on your research, will give them 170% back in growth of their domestic product. So nearly 3 times as much of the money you get back, because this gets on top of the investment that you get back. But okay, how do we do it? I mean, we've dreamt of flying for millennia already. You know probably the myth of Ikaros, as we say in Greek. And if you consider that people already dreamt of flying for millennia, I think it's surprising that we only have been able to do this for, what, say about 100 years. Why is that? Why wasn't it possible before? We sailed, we built bridges, high buildings, we had a lot of transport already functioning, but flying was rather late. Some even doubted. Lord Kelvin, not the least of the scientists, at the beginning of the 20th century, said it was physically impossible to fly with anything heavier than air, which is strange if you consider that birds already existed. But of course, it's still a difficult trick to do. We all know the sketches by Leonardo da Vinci, one of our heroes. And he really tried to tackle it in a more technological way, and he understood a lot about flying, but still, his designs were impossible to manufacture in those days. So, the 20th century was when it really started, and is often called the century of flight. I hope there will be more centuries of flight, of course, but this was the first century of flight, let's call it that. And we'll use this sort of storyline in the lectures as well. So you will see many of these aircraft that you see on the slide right now, you will see them coming by in the lectures as examples. The Wright brothers, of course, famous example. You also see 2 wars that spurred a lot of technological innovation. In the beginning, the only real use for aviation was, apart from the rich people, was the military purposes. They helped develop the aeronautics very fast. And then only in the second half of the 20th century, mass tourism in the air really took off. So, it was very hard to fly, apparently, for many centuries. But still, there are many ways to fly. In general, there are sort of 3 principles to counter gravity. Any ideas? How can you counter gravity? Buoyancy, right? Being lighter than air. A balloon with helium or hot air. 2 other principles. Lift. Yeah, lift is the result, but how do we generate it? Thrust. Yeah, it's so just a force which you normally use mainly horizontally, but you could use it vertically. But still, the principle, how to generate lift. How do you generate this thrust, vertical thrust or lift? Shape of the wing. Yeah, that's one way to do it. If you name it more general, there are 3 general principles. Pressure. Yeah, it's a way to phrase it. If you zoom out a little bit more than the shape of the wing or the pressure over wing, there are 3 general principles. One is being lighter than air, with helium or hot air. Second is push air downwards. That's what you do with the wing, which generates a pressure difference, but the net result is that you push air down, or a rotor does the same thing. And the other thing is push something else downwards, as a rocket does, for instance. They burn something and the gas they emit. Those are the 3, not the only, but the 3 principles that we normally use to fly. Well, the third one I leave for the second period, for the space guys. And we'll focus on the first 2, starting with the first today. Helium, hot air, but there are of course other ways. Floating by being lighter. Because I called the 20th century the century of flight. But this was not the first century of flight. In fact, the principle of hot air balloons was already known just after the beginning of our, around Christ, two centuries, 200, 300, the Chinese already used hot air balloons. A bit similar to the ones that you can now buy to celebrate the New Year's evening. And they are responsible for many UFO reports in the Netherlands, I think. And they use something burning to heat the air. And they were used, according to documentation, for military communications. I can imagine that as sort of beacon, but also surveillance, which puzzles me, because how can you use it for surveillance? Maybe send up many and this will light the enemy troops or something? I don't know. They didn't put a man in it, as far as I know, or at least no one that survived to tell. Because this really happened much later, in the 18th century, by two brothers again. Many innovations happened by brothers. You have the Wright brothers, but the first real flights were done by the Montgolfier brothers. And they really were brothers. Sometimes in the past they called two men living together brothers, but they really were brothers. Joseph was the oldest one. Etienne was the younger one, the 12th and 15th child of a manufacturer of wallpaper. And Joseph was really the wild one. He once studied a fire and saw, when the laundry was drying over the fire, saw some of the laundry blowing up like a balloon, and figured, hey, if you could get from the air, get men in the air and via the air to other troops, you can perhaps take fortresses that normally are hard to take. Etienne was a different kind of guy, not a maverick type, but more the technological, the scientific type. And together, that was a really good team. You see the same with the Wright brothers, those two characters. One the really inventor type, maverick type, wild guy, the other one more the 4-0 guy, and this balance apparently gets a lot of things done. And they set up to do this in a really scientific or technology, scientific way. They did experiments first, and larger, first indoors, later outdoors. And before they put men underneath a hot air balloon, they tried it with a duck, a rooster, and a sheep. This was not some random collection available in the nearby farm, but this was really a scientifically set up experiment. Any ideas why they chose those three animals? Weight differences? No, could have been, but that's not the case.
Well,
the duck could fly, yes.
The chicken might not die if it fell down. The sheep was delicious if it fell down.
So it was chance of survivability when it fell down. No, the idea was they didn't know what happened when you got up to altitude. They thought even with mountains or something, maybe there's a specific kind of gas close to the ground, which is not available if you go higher in the atmosphere. Well, ducks can fly. So they clearly can stand these strange gases or lack of gas higher in the atmosphere. So they were sort of control group that if something happened to the duck, it must have been the craft and not the fact that they were high. Then the rooster was, of course, is a bird, has the same physiology, but doesn't fly too high. So there you could see whether it was caused by bird physiology or by the fact that you are used to it, used to fly. And of course the sheep is the model human, a mammal, and if they survived, probably a man would. So that's why they chose those three animals. They flew, they all survived. I think the sheep broke his leg during the crash landing, but apart from that, they all survived. And they were it was the first mammal to fly. And then the king said, because the king was by this time involved and raised a lot of interest, it was done at Versailles, this demonstration. The king then said, okay, let's get some prisoners now and put them underneath the balloon. And that was the moment when a physician and an army officer said, well, you could do that, Your Majesty, but maybe there are other people who would volunteer, and well, we would like to be the first one to fly, actually. So that's what happened, even though if you look really careful, Etienne Golfier was really the first one that flew, but his flight was still tethered, so there was still a wire between the balloon and the ground. So the first free flight was 21st of November, 1783, with those two people on board. And especially Jean-François Pilatre de Rogier has made a lot of flights since then, because remember, 1783, more than a century before the Wright brothers. So for a complete century, ballooning was the only way to fly. And there were a lot of adventurous pioneers in those days that did it in the beginning. It was a really hazardous thing to do. A lot of experiments. You see on the lower right a balloon which had control surfaces to steer it depending on the wind. If you know a bit about physics, you'll know that will never work. And a lot of dangers as well. A lot of people died. Also, Jean-Pilatre de Roger died in one of the flights. Some crashed in the sea. But still, people dreamt about future applications of balloons, and they thought this was the way aircraft would look in the future. And the beginning of the 20th century, of course, saw the Zeppelin, the more streamlined shape of a balloon with propulsion added to it. But the damage of this whole development, the whole class of aircraft, was destroyed by the disaster with the Hindenburg Zeppelin, which was filled with hydrogen caused by a lack of helium in Germany due to the war. And hydrogen is very good, it provides more lift even than helium, but it is, of course, very inflammable. Well, you see that today's balloons are in principle the same. You see the shape on the left, or the more streamlined, rigid airship on the right. And you also see helium and hot air as the two main gases that are used for ballooning. And even the combinations are sometimes used, for instance, in the Spirit of Freedom that was used for a record flight. So why do we need other aircraft? Why not stick to ballooning? I mean, it gives you lift in a very efficient way, a green way. And it can go very high, higher than a conventional aircraft. So what are the drawbacks of a balloon? Slow, that's one. Say again? The?
Dependence on the wind.
Dependence on the wind. Okay, but we could just make a really very good propulsion system added to the Zeppelin. So very powerful engines underneath. Then this could solve everything, right? Make it fast. Exactly. There's a huge volume that you need. And you get a lot of drag, a lot of resistance from the air if you want to go fast. And it is?
Still too big for military applications.
And too big for military applications, right. The main reason that we... Say again? It doesn't? Carry a lot of mass. Well, that's just a matter of scaling it up. But you get it through. It is quite, if you look at this picture, indeed compared to a wing, it's quite large compared to the amount of mass that you can carry. That's right. So in that sense, it doesn't seem that efficient. It's often still, sometimes the airship is still mentioned as a very green way of transport, but as I think you noticed, with the high drag, it is not a very green way. If you want to travel, the amount of work that you need from the engine and also the emission or fuel that you consume is, of course, dependent on the force that you need to generate times the way that you travel. And this force is very high. So overall, the energy you consume for traveling by airship, it makes it, unless you fly extremely slow, not a very green way for transport. So that's why even today with emissions and oil scarcity, you will not see the airship as the final solution. Some say a combination should be possible, but still. So how does a balloon provide lift? Buoyancy. Yeah, but that's just the same as saying it provides lift. Right? So, but still, what is the general principle? High pressure inside, high pressure in. Other air is lighter. Yeah, but that means it goes up, right? We knew that. The question is why? Density. Yeah, and that makes it lighter. But still, if you, for instance, if you look here, this is, you're right, you're all right, of course, but I'm looking for a sort of deeper explanation. This is a balloon with helium, and the inside and outside does not move, it stays the same size, right? So if we look at a little bit of the balloon, there is apparently equilibrium between the inside and the outside. So I could say there's equilibrium all around the balloon, so it should not go up. Still it does. There's? The air goes down when the balloon goes up. Yeah. There's another question you could ask. Why is helium and hot air both used today? Why not one of the two is probably better, right? It's also... So let's study it a bit further, because this is a good introduction to knowing the atmosphere and gases. So let's study it a bit closer. And for that, we're going to need something that you should know at high school. By the way, I made a little handout here with some formulas that you need in the first few lectures of stuff you still remember anyway from high school. I hope. Well, one law that we need is, of course, the gas law. And the other one that we clearly need is the law of gravity. I hope this all looks still familiar after the long summer vacation. Pressure times volume is equal times n, the number of moles of a gas, times the general gas constant, times the temperature in Kelvin. Law of gravity is mass times the gravity acceleration. There is a problem with this gas law, as you have learned it in high school, because this works very well for a certain volume, but if you talk about the atmosphere, nobody knows the volume of the atmosphere, because this sort of gradually dissipates when you go into space. So we normally want to look at certain points in the flow. Even if we study 1 cubic meter, still we have a problem when this air moves over the wing and we want to study smaller parts. So instead of volume and the number n, we would really like something else, that we can really say that at a certain point, or at least very small quantity, gives the state of the gas, like air density. So instead of volume and n, we would like to have air density. So let's change this formula. We know that the air density is given by mass divided by volume, which means that the volume is mass divided by density. So let's substitute that and say P times m divided by the density. And then we have taken out the volume, but now we have got the mass. And also we want to get rid of the n. Well, what is n? N is the number of moles. You could also say it's the mass divided by the molar mass, the mass of 1 mole. And that's of course the same as n. So if we substitute that as well, we get m divided by the molar mass times r times t. And this is nice, because if we divide by the mass now, left and right, we got rid of that one already. And which means we can also write this as P is rho times R divided by the molar mass times the temperature. And most of the times we will be talking about air. And that means that R divided by M, well, air is a mixture. And we will be talking about the same R and same M all the time. So in aerospace or in aeronautics, you often see R given for air only. And what we then basically do is that we call this R a different R. And we just put a little curls on this, as Mr. Anderson has done in his book, to make the distinguishment between the two different types of R's that we use. We call the R for air, we take the general gas constant, which is 8 point something, 3145, divided by the molar mass, and that is in sort of average, because we're talking about different gases here. So CO2 is very heavy, while O2 is lighter, and N2. So this is, most of it of course is nitrogen, and so it's very close to nitrogen. It's 29.97, which means the R that we will use most of the times is 287. Oh, this is, I should make it, this is gram per mole, so to be correct, I should do it like this, and you should forget about the point there. This is easier for me to do than in your notes, but Okay. So 287 is the gas constant that we normally use, which means that the gas law that we will normally use looks like this. P, the pressure, is air density times R times T. But never forget that this R is specific for air only. So it's not the general gas constant. R is for air only. If we compare different gases, if we're going to talk about balloons with helium, for instance, then we will need the formula one above that, with the curly R divided by the molar mass. So that's the new gas law that we use. Now with this, a balloon. There's the test of the pen. Okay, so what makes a balloon fly? Archimedes was actually the first one who really understood it. It's the law of Archimedes, so the buoyancy law basically, which makes it fly. But let's look at it in a more physical way. If we have air around here, this is the atmosphere, we have a certain amount of air. Imagine then we look at one specific volume of, no, that's not what I want. Let's look at one specific volume of air. So it's still air, but has by coincidence the volume, the shape of a balloon. And if we look at this situation, and the atmosphere is in equilibrium, that means that if we cut it out, if we would take away the air, we would take the same shape, and we look at the air around it, now we've taken out the air, then what is the force if you would integrate, if you would sum all the forces of the shape around this empty volume now, what would be the sum of those forces? 0, I hear some say? No, it's not 0. It would be equal to the weight of the air that once was there. Because if on the left side there's equilibrium, everything stays the same, it means that the surrounding air carries the air in that volume. So even without knowing the exact shape or the exact force distribution over the balloon, we would know that the resulting force on this volume would be, sort of the lift force, would be equal to the amount, the weight of the amount of air that was in this volume. So this lift force, this maximum lift force, would be, let's call it FL, would be the mass of the air that we have taken out times G. Don't go. Up or down? Sorry. For your writing, right. So the force would be the mass of the air times the gravity acceleration. And the mass of the air is, of course, equal to the rho, the density of the air, times the volume that we've taken out, times the G. So this is the sort of maximum lift we could get out of the atmosphere in this, using this principle of this volume. But of course, in return, we get the weight of the balloon, or the gas that we have used in the balloon. And so the net lift would be less. And this would be again this rho, let's call it the rho of the atmosphere, times the volume times G, minus the rho of the gas times the volume times G. So here we see indeed a difference in density causing the lift. We could rewrite this by saying we have the rho of the atmosphere times the volume times G times 1 minus rho gas divided by rho atmosphere. So here you see basically that the net lift is the gross lift indicated by the 1 here, rho atmosphere V times G, but you lose a little caused by the ratio between the densities of the gas and the atmosphere. This gas could be hot air or helium. So if we want to know which balloon is better, hot air or helium, we should just fill in the properties of helium versus air and hot air versus the atmospheric air to see the net effect. So let's first look at helium. So we have the net lift, and we have said the lift is equal to 1 minus rho gas divided by rho atmosphere. Well, we have also made this new gas law. Let's take the one for different gases. That says P is rho times R divided by M, it's the curly R, times T. And if you look at this, you can also rewrite it to say that the density is basically P times M divided by R times T. So here we see that the ratio of the two densities is equal to the ratio of these quantities, Pm divided by RT. Well, if we look at a helium balloon, then we can assume safely that the T is about the same, right? The temperature inside, outside is the same. The pressure, would it be the same inside or outside the balloon? No, in general not. But you would probably be surprised to find out that the difference between the pressure and inside and outside the balloon is nearly negligible. It's in the order of a single percent, 1 or 2%. It's really minimal. It has to do with the enormous quantity of the air pressure around us. It's really, really very minimal. So it's a rather good approximation to divide the two and say that P, R, and T are all the same, and that you basically get the lift mainly from the difference in molar mass. V times G. Air, atmosphere or air. And if we then look at the actual quantities, for instance for helium, the molar mass of helium is 4.00 gram per mole, while for air it's 28.97 gram per mole. So if you divide the two, you get about 1/7, a bit less. So which means that 1 minus 1/7, which means that this would be about 6/7 the total, which means that 6/7 part of the weight of air is what we can get as lift with helium. So that's quite a lot. It's about 86%. And of course here you can also see the effect of different types of gas. If we use, for instance, let me see, I've got it somewhere here. If you use hydrogen, the molar mass of hydrogen is only 2. It's 2. Of course, it has molecules of 2 atoms, otherwise it would have been 1. But so it's 2.2 gram per mole. So hydrogen is even better in providing lift than helium, but we know the drawbacks also from the Hindenburg. So we use a lot of helium. In fact, I'm going to do a little experiment later to check our calculation with these helium balloons. So we can get helium. Where do we get helium? How do we get helium? You know it? Where does helium come from? It is a gas that doesn't bind itself to other molecules, so we cannot just break something apart to get helium. Sorry? Freeze it off? Yeah, lower the temperature of the air and get it out of the atmosphere. There is a little fraction of helium in the atmosphere, But there's another way. Distillation? Fractional distillation. Yeah, that's basically the same as what you're saying. Just so get it out of the atmosphere in the end, right? Yeah, you could do that. I think some of it's one way to get helium. Another way is that if you look at radioactive decay, one of the types of radiation that you can get is alpha radiation. And if you look up alpha rays, those are actually helium cores. So they expel a helium core, which easily picks up an electron, and this is how you get helium, which immediately flows to the edge of the atmosphere, so you've lost it. That's why there's only a minimal amount in the atmosphere around us. But that doesn't happen if it's trapped in a cave. So most of the helium today comes from the United States, where they have caves, where due to radioactive decay, you get helium in the caves, which you can extract. But it's getting less and less and less. And I wonder whether we will still have it in like 10, 20 years, whether we will still have helium balloons around. I suggest we take a little break here, and then we test our calculation by verifying the lift force of this set of balloons here. By a gas, by a different gas than air, we still have to look at how it relates to hot air, how you compare helium lift with the lift of hot air, and why we use both. And also I got a question over the break. The mass of air, is it the air around the volume or inside the balloon? When I replace the gas of the air by the gas, I look at the weight of the air that we have taken out. And because that should be equal to the force on this volume, because this air was not moving. And then, of course, assuming that the air is the same around the balloon as it was at the volume where the balloon was, that's why we use atmosphere and air at the same time. So we've seen this. So how does it look for hot air? We're going to look at that first. Then we're going to test whether theory also matches practice by seeing what the weight is that those balloons can lift, and on the side see how many of those balloons you would need to make a little flight yourself. And then we will look also at some examples of what you can do with helium balloons and some event that will happen this weekend. So first, hot air. What we've done here on the upper side of this sheet doesn't work for hot air, because here this is probably still okay, but here we would have 1, because the molar mass of hot air is the same as the molar mass of cold air. So this formula doesn't work for hot air. And this is not a surprise, because we derived this formula by assuming that the T was the same inside and outside the balloon. So how would this look for hot air? In that case, we again divide the densities of the hot air with the cold air around it, because this still goes. But if we then look at what happens when we divide the two densities, then we have an identical molar mass, so that disappears. We have also a nearly identical pressure, because the downside of a hot air balloon is often open, so if there would be a pressure difference, it would be immediately compensated by air flowing out. R is the same, so everything is again the same except for the T. So this ratio, gas divided by atmosphere, would be replaced by the ratio of the temperatures, but inversed. So we can substitute the rho's by the temperature. Inversed. So again, rho atmosphere times V times G times 1 minus T atmosphere divided by T hot air, the gas. Okay, prima. So divided by T atmosphere divided by T hot air. And normally we do not talk about the temperature in Kelvin. We often talk about the extra temperature that we have added to the balloon. So maybe it's easier to say we have the rho of the atmosphere, we have the Vg, and we have 1 minus the temperature outside and the temperature of the hot air balloon where we have added a delta T. And this we can simplify by saying 1 is the same as T plus delta T divided by T plus delta T minus T divided by T plus delta T. And this would be equal to rho atmosphere times V times T times the increase of temperature divided by the temperature plus the increase of temperature. So here we see the formula, the lift formula for hot air. And we see now that the ratio of molar masses is replaced by the ratio of the increase of temperature over the temperature plus the increase of temperature. Now, if we now compare helium with hot air, then we say that this, if we want to have the same lift with hot air as with helium, then this should be equal to 6/7. Which means that if you, well, you could also write it here. If we say 6/7 is equal to delta T over T plus delta T, we can, by multiplying on both sides, the diagonals, we can say that 6 times T plus delta T is 7 times delta T. If we take away the brackets, 6T plus 6 delta T is 7 delta T. In other words, 6T is delta T. Still following me so far? 6T is delta T. That means that the increase of temperature of the air that we need if we want the same lift as helium should be 6 times the temperature. And that's the temperature in Kelvin. So which is often close to 300 Kelvin, like 15, 20 degrees. You're close to 288, 293 Kelvin. Let's say, to get a sort of feeling of the order of magnitude, let's say about 300 Kelvin. That means we need an increase of temperature of 6 times 300, 1800 Kelvin. So it means the temperature of the hot air inside should be close to 2000 degrees Kelvin, or 1800 degrees Celsius, or 2100 Kelvin, 1800 degrees Celsius, which is the temperature of a blowtorch. So that's not something your hot air balloon would survive. So on average, this clearly shows that helium is much better at providing lift than hot air. But there are two advantages of hot air. First, you can control it. You can later add it using a burner. And the other one is, and the main advantage is that it's much cheaper than helium. So this is all theory. Let's see if it really works. I've got some helium balloons there. They should be around 45 helium balloons. And let's first calculate the lift that the party balloons should be able to generate, and then test it. It is on the side. We'll also give you the information how many party balloons you need to buy to fly. Always useful. So let's see. The manufacturer of the helium balloons said they were 14 liters. But he also said they were equal to a sphere of about 11 inches in diameter. Those two are contradictory, and it wouldn't be a surprise that if you really calculate it, it's less than he actually promised. So, one party balloon is said to have a diameter of 11 inches, which is 27.94 centimeters, which means a radius of, let's carry a bit of digits with us to be on the safe side, radius of 14 centimeters. And let's work in SI units to avoid problems later down. The volume of a sphere, was it on the slide? Things you need to know and stuff? Don't think so. Anybody knows? Volume of a sphere? Yeah, I hear it immediately. Very good. 4 divided by 3 times pi times the radius to the power 3. If you fill in these values, you get, in SI units, you get 0.0114 cubic meters, which equals 11.4 liters instead of 14, as the manufacturer said. So I should get some money back, I guess. Then the lift. Well, we can now calculate the lift of one balloon, because the only thing we need for this formula is the type of gas that we have, so we know the molar mass, and we need the volume. So let's see. The lift of the balloon is rho atmosphere times g times v times 1 minus mass of the gas, molar mass of the gas, and molar mass of the air. So, what is the density of the atmosphere today? Yeah, about, but let's I checked my little weather app on my iPhone this morning, and that said the pressure today was 19.4 hectopascal. I guess the temperature in this room is, well, what shall we say? 19 degrees Celsius. Used to be 18, but because of all the hard work, it's now 19. So that's about 292 Kelvin. The density, then, we can calculate P divided by RT, and this should be, and now we have to be careful to use SI units. This should be Newton per square meters, because it's hectopascal on the other side, so we multiply by 100, and then we get the Pascal or Newton per square meters. The R, which R do we need here? The 8.31 or the 287? 287 is indeed the one we need. And the temperature, 292. Anybody got a calculator here? It's a bit difficult out of the top of my head. I don't have the current pressure here, so if somebody could provide the answer. And we've used SI units. And it's also important, as soon as you substitute values in a formula, always make sure you have SI units. You saw me previous doing it wrong, basically. You saw 4 divided by 28, those were grams per mole. But with a ratio, that doesn't matter, of course. Okay, I hear some numbers. What is it? 1.204. Okay. The standard value we will later use for a standard atmosphere is 1.225. So this seems to be in the right order of magnitude. So 1.204. Then, what else do we need? We've got G. We'll use 9.81. So let's see how far we get. The lift of one balloon is 1.204 times 9.81 times the volume, 0.114. What's the other way to get rid of it? So then times 1 minus 4 divided by 28.97. So this would be the lift in Newton of one party balloon. I hope you didn't put away your calculators. It also would tell me whether it's safe to make that loose, those balloons, or whether I will be stuck to the ceiling here. How much? 0.12. 0.116. A few more digits. 1. Okay, so that's 102. Let's take 4. Newton. So if we want to know the weight of the mass that we can put underneath, what do we do then? Divided by g. So could you divide by 9.81? One. So say again. 1184 kilogram. So that is 11.84 gram. So each party balloon can carry close to 12 grams. Should we? Compensate for the weight of the balloon, yes, of course. This is assuming the balloon itself weighs nothing. So that is indeed one of the errors that we made. So we'll have to assume that it's actually a bit less. But let's test it. Those are 45 balloons. So if we do this times 45, what is the weight that we get? 532.8 gram. So that is about half a liter of water and a bit more. Let's see. Let's first add half a liter of water. I need some assistance here, so could you come forward and help me with untying? Yeah, you. You need to be at the corners, you noticed, right? Okay, so if you can keep this. Well, you can see it's, you knew it's safe, right? You weigh more than 500 grams. Even kijken hoor. Scissors. So it should at least be able to lift one bottle of water. And then we should still have a little. Okay, let's see. Hold on. Okay. Hey. So what did we forget? I think we already heard one error. That is indeed the weight of the balloons. So we have to think of a storyline to match 30 grams, right? So weight of the balloons. That's one. Weight of the bottle and the strings, yes. There's more, I think. Sorry? The balloons? Yeah, that's right. Some balloons might be smaller. There's one more error that we made. The helium escaped a little already. That's also true. If I'm going to do this again Wednesday for the Dutch group, I need new balloons. Yeah? The balloon is? Balloon is not round, so maybe a little bit of extra, but that would generate extra lift, because then we would have more helium. But it's true that we've made an approximation in the shape of the balloon. That's right.
Maybe our calculations are wrong. Maybe he's actually right about 14 liters.
No. Well, then it would have been more. He says maybe we're right of about 14 liters. But
Really wrong.
really, really wrong. No, it's not really, really wrong. I wouldn't have done it here then. One other thing is that, remember that we said that the pressure inside and outside is approximately the same. That is also an approximately. Of course, to compensate for to keep the shape, we got a little bit of higher pressure, this 1 or 2%. Also, that's the error we also made, which we noticed along the way, but also could generate 5 extra gram here. So this all together, of course, creates this error, and also the amount of helium that we got. Maybe I can even get more money back, because I really doubt whether all the things that we mentioned whether they add up to 32 grams. If you imagine taking out all the helium, taking out all the water, would that weigh 32 grams? Maybe. But at least the order of magnitude seems to be right, so those formula seem to be working in that respect. Also the temperature in the room, by the way, we mentioned that was also an approximation. So how many balloons do you need to make a flight? Calculators again, any idea? Those are 45, clearly not enough. So before the summer vacation I weighed about 80 kilograms. So how many balloons would I? About 7,000 balloons, yeah, that's right. And after the summer vacation there was more than 300 balloons extra needed to get me up in the air. So, what have we seen? We've seen helium is much more powerful than hot air. We've seen that with this new gas law, which we call the equation of state, P is the rho times R times T, or R divided by the molar mass, that we can very quickly calculate properties without knowing the quantity. And that's the useful aspect of P is rho RT. And you should know that one really by heart because you're going to need it a lot in all these aerodynamics calculations. With helium, such a powerful lift generator, you also may wonder, how do you really go up? And there's also one question that we didn't answer yet, and that was, if we assume, or if we see that the balloon isn't getting larger or smaller, this shows an equilibrium on every part of the balloon. And still it goes up. We've calculated it by taking again the overall view, looking at the weight of this air that we took out, and that's again the overall view. It still doesn't explain, in terms of forces, what is really happening. So which force is really pushing this up? How would you explain it in terms of force? If you really look at the balloon as a structure made of all of little pieces together forming a balloon, where is the lift force? It's all pushed. It's pushed up. Of course, it's the integration of all the forces around the surface of the balloon. But if you really think about it, it's actually the pressure difference in the atmosphere at this altitude and at this altitude that causes the balloon to lift. You know that the pressure gets less when you go to the mountains. If you dare unwrap certain bottles, they will all have been crinkled if you go skiing. But there is already at this distance, there is a larger pressure here than here. And that is really the force. So this volume feels a higher pressure underneath the balloon than on the top side of the balloon. So there's way less pressure in the back of the audience here. You've got way less air there than the people here. That's the bright looks I get here. You have to work much harder there to get the same amount of oxygen. But imagine, only at this distance already a pressure difference in the atmosphere. And that is because, of course, our atmosphere is a sort of ocean of air and we live at the bottom. And the pressure is huge. And minor differences in air pressure already create a lot of force. Helium also would like to go above the air. So if you go higher with helium and you allow the balloon to expand, so to match the pressure of the inside and the outside, if you have a very floppy balloon, as they use, the weather balloons for instance, they are hardly filled. So they're huge balloons, but there's a little bit of helium inside. And when it goes up, it very quickly expands to match the pressure inside and outside. And this helium will continue to go up as long as there's air around it. Independent of pressure, temperature, it will continue to rise. So, in theory, helium balloons should be able to get you to space because it wants to get out of the air. This is not just true in theory. In fact, if you would do it like a student from 3ME did, Tim Zaman, he last year bought a weather balloon and a bit of helium, attached a camera to it, standard camera, and just let it go. Well, you also want to get it back probably. So it's a bit more complex project than just like that, but still, for about 200 euros, he was able to get a balloon up to the altitude of 100,000 feet, about 30 kilometers, and make pictures like this. And I mean, this nearly looks like it's made out of the space shuttle, right? You see the dark space, you see the curvature of the air, and you even see the atmosphere. The blue dispersion is the little particles in the air, is the indication of the atmosphere getting less. So for 200 euros, you can make pictures from space, the edge of the atmosphere. And in fact, you see the website here, mentioned underneath, hollandshoogte.nl. This weekend, there will be another attempt, and then there will be a live feed with a camera, which is attached to the internet, so you can live watch a balloon here in Delft go up to space, and we will have a radio station on the top of our building, of our faculty, to hopefully bring you the live feed from the edge of the atmosphere. Here you see another picture. You see the Waddeneilanden, the islands in the North Sea. Really spectacular images. So helium does indeed bring you much higher than aircraft can get. There are also people that try to fly with helium balloons, the party balloons. For instance, a priest in South America, I think it was Argentina, who also made the little calculation of how much balloons do you need. And that's quite a lot. As you can see, he used much larger balloons, so they have less loss due to the weight of the balloon themselves. And he had about, I think it was 5,000, 7,000 larger balloons that he actually needed, which very quickly brought him up. He is a priest, but he's also a stuntman in his spare time. And it's an odd combination, but happens in South America. And he did this before, so he had experience with flying with balloons. But in this time, he wanted to raise money for a little chapel for truck drivers along the highway. And you see this structure here. It is made very vertical for a reason. Because what happens when this goes up? What happens? Exactly. That is the answer to my question, yes. So the pressure here is much higher than here. So when this goes up, the pressure gets less very quickly. And the top balloons will be the first ones to burst, to explode, because there's a maximum volume that a balloon can handle. And if there's even a tiny pressure difference, it will start to increase to match nearly the pressure outside. So the green ones will be the first to burst. And this will automatically create a sort of equilibrium at some point, because you will lose balloons, and at some point you will then have reached your cruise altitude, and then you will fly with the wind. You need to know the weather, of course, but that's never fully predictable. So he went up. I can have a little clip of that, I think. He went up. Cannot open specified file. Well, forget about it. He went up and then quickly disappeared into the clouds. And that was the last we ever saw of Priest Adelier. So it was a big mystery. What had happened to Priest Adelier? He went to meet St. Peter, well, in the end. But at some point around the internet, there were pictures where you saw him flying behind the Eiffel Tower or the White House. There was a lot of speculation. Most of those pictures were photoshopped. But what really happened to him, that the weather forecast is not 100% reliable. So in this case, the depression took a turn a bit more to the west than they anticipated. And instead of going inland, he was sent out over the ocean. So after a while, they found this. And the color of the balloons indicate it must have been from the lower section. So that's not a good sign. But still no Priest Adelier. And I think really months later, they also found him washed ashore. So it's a real pity. He did not survive. There was another man who had a similar approach, who did it in California, and really disrupted air traffic in Los Angeles. And he had a little gun with him, so he could shoot balloons to control the altitude. And he had a lot of soda cans with him to drop if you want to go higher. Okay, so helium is indeed a way to fly, but we've seen many disadvantages already as well. So, this altitude, the pressure difference. Let's study the atmosphere a bit more. If you see what we have done, we've basically looked at a law which is known as the hydrostatic law. Of course, we prefer to call it the aerostatic law, but it's the same. And that has to do with the change of pressure due to altitude. And this is the main driving force of the pressure difference in the atmosphere. So why do we have high pressure here? That's because we are on the bottom of the air ocean, the floor of the air ocean. So you know, we saw the number earlier, about 10 to the 5th Newton per square meter is it's actually the standard atmosphere has a sort of average, which is 101325, is the standard average atmospheric pressure at sea level that we normally use. And we've also taken a standard temperature, which is 15 degrees Celsius, which means 288, if you want to be exact, 0.15 Kelvin. And the standard air density is 1.225 kilogram per cubic meters. These are standard values at sea level that we use in a standard atmosphere. So we have designed a sort of ideal atmosphere for our calculations, an average atmosphere as well, matches the atmosphere at moderate latitudes. And this has these properties. And then we need to know what happens when you go up. Well, there are two laws that we need to take into account. We have P is rho RT, and we have the gravity force is m times g. So these two forces are sort of, to make our standard atmosphere physically correct, this needs to obey those two laws. But also means that we want to know 3 properties at altitudes, but we only have 2 laws, which means we need to fix one, and then we can calculate the other ones. So how do we do that? Well, the first thing that we do is we fix the temperature. So in our standard atmosphere, we take the average reduction of temperature that you get when you go up in the atmosphere. Does anybody know why it gets colder when you go higher? The sort of naive question is, of course, you get closer to the sun, so it should be hotter. But it gets colder. Why is that? In fact, what happens is that the heat radiation, the infrared of the sun, goes through the atmosphere. The atmosphere is nearly transparent for those rays. Hits the Earth. The Earth is heated, and by the contact that there is between the air and the Earth, there's a higher temperature. And this, of course, becomes less when you are further away from the Earth. On average, the temperature decreases 6.5 degrees if you go 1 kilometer up in the lowest part of the atmosphere. So if we look at the atmosphere, our standard atmosphere, we see at the first layer, the troposphere, as we call it, we see the temperature sharply go down up to 10 or actually 11 kilometers. 6.5 degrees Celsius or Kelvin per kilometer. So this means at sea level, if we have a temperature of a nice 20 degrees, if somebody builds a mountain in the Netherlands of 2 kilometers high, which is a current plan by somebody, then it will be 13 degrees colder on the top. So if it's around freezing point, it will already be minus 13 on the top. So chances for skiing in the winter are high if we build a mountain of 2,000 meters in the Netherlands. This is a troposphere up to 11 kilometers. But the strange thing is that then, in the troposphere, the temperature becomes constant for a little while. And this, of course, is sort of average of the real atmosphere. In real life atmosphere, it's different every day. But the average is indeed sort equal to this. So then for 9 kilometers, there is no change in temperature, and then it even goes up. What's happening there? Different gas. That is true, and then?
Different thermal absorption.
I hear the right word there somewhere. The ozone layer, indeed. There you have a layer of ozone. Because of the type of rays that you get in the atmosphere, they change the oxygen and make it more radical and make the O3, the ozone molecule. But this molecule also stops the radiation, blocks the radiation. But of course the energy has to go somewhere. And the default thing that always happens to energy, if you lose it somewhere in some physical experiment, is that it becomes heat. So that's what happens here. This is where the ozone layer is, and we get a lot of increase of temperature again. And then again it decreases, and apparently here there's another type of rays, but it's very hard to discuss the temperature above 100 kilometers, because as we will soon see, there's not so much air anymore there. Here you can see how quickly the pressure decreases if you go up. And also, if you see at 11 kilometers, and this is where you typically fly in cruise flight with a Boeing 747, for instance. You fly just in the stratosphere and just above the troposphere. Then the pressure is 22.6 hectopascal, which means that over 75% of the atmosphere is already below you there in mass, because the pressure is caused by the weight of the air above you. So if we take at sea level here 10 to the fifth Newton per square meters, so if we take 1 square meter, let's say this, there's 10 to the 5th Newton pushing on this square meter, and that is the same as 10 to the 4th kilograms. In other words, 10,000 kilograms of air is pushing on 1 square meter of desk here. 10,000 kilograms. This also means that if we have made a wing or some other shapes, and if we create between the top side of this desk and the side underneath, if we create a pressure difference of only 1%, we will have a lift of 100 kilograms already in this 1 square meters to carry. That's more than most of us weigh. So, in fact, 1% of pressure difference is already enough to get a lift force of 100 kilograms. So this is one of the reasons why we're able to generate lift with air. The pressure, the air pressure, is really immense. And normally we don't notice it because it's also pushing on the side underneath and it's on all sides, so we're used to it. But you only notice it when you have a vacuum. If, even steel oil barrels will wrinkle if you take out the air. And you can see clips on YouTube showing the effect. It's really immense, the force that the air pressure around us has. So just minimal differences in air pressure will create huge lift forces already. But that's how wings do it, not how we do it with balloons. I want to have a look at one more law, basically more general law of aerostatics, which is responsible for the change in the pressure in the temperature in the atmosphere. So let's take one disk of air. Other screen, yes. One disk of air, which has a surface, let's call it A for area. Underneath, there's a pressure P, and then the pressure on the top side we call, let's see, P plus delta P. Let's see, get the signs right. P, so a changed pressure P plus delta P. the altitude is delta H. So here we see a little disk of air inside our model atmosphere to see what happens. So what are the forces that we have here? Well, we have a force up, which is P times the area. And this should, if there's equilibrium, and we want equilibrium in the atmosphere, should be equal to the pressure that is pushing down on the other side, P plus delta P times A. And there's a third force on our disk of air. What's the third force? Gravity. Also going down, and m times g. And m times g is the same as rho times volume times g. And that's the same as rho times the area times the difference in altitude times g. So we add that. So we can now see that we can divide by the area. So it doesn't matter apparently how wide this disk is that we take. And then we get P is equal to P plus delta P plus rho delta H times G. Then we can take out the P as well. And we can bring the delta P to the other side by saying delta P is, we get a minus sign in it. I'll carry this on this side, times G. So this is, in effect, the aerostatic or hydrostatic law explaining the decrease in pressure if you go up by the law of gravity. We normally write it differently. We write it as such. We say dP is minus rho g dH. So instead of a delta, we write a d, indicating a very small delta. Because also all kind of things happen within this disk. The pressure changes perhaps, and I mean there's also gravity inside the disk. And we've ignored that. We only looked on the outside and assumed it as one volume. But if you want to know the change, then you should look at really small deltas and add them up through the atmosphere to see the effect over larger altitude. So that's how you get the formula which you already saw here, but the minus sign is missing there. So this law, the hydrostatic law, is in fact the one that's causing the decrease of atmosphere. You also see that the delta P is negative, which shows the decrease of pressure if you go up. Next time we will use this together with the gas law to explain the complete change of all the properties in the atmosphere and check out what the circumstances are at 30 kilometers height where Tim Saman will send his camera. And that will be tomorrow. One more thing, homework. Oh, yeah, right. So, for next time, which is tomorrow, I would like you to do 3 things. I've got a handout here on ballooning, because that's not in Anderson. There are 6 exercises, 6 problems in there which you can try, which you should try. Also, if you want to use this new gas law, equation of states, you can try the problems of chapter 2 of Anderson. That's 2.1, 2.7, and 2.11. And optional, you can also take 2.12, 13, and 14. Note that in 2.11, Mr. Anderson is very fond of using imperial units. So he uses very exotic units sometimes. For instance, the slug per feet to the third. The actual value of that is, if you translate it to SI units, it's 515.4. That's something you also can find on the internet if you want. Also, if you read Mr. Anderson's book, he will say that he thinks it's very important that you know all these imperial units and all these aeronautical units. I have a different view of that. Normally, you will get everything in SI units, and if we use different units, they will be given. So you can, because this is something you can easily look up. And we always calculate with SI units here, and I expect you to do the same on your exam. This will avoid problems. And also what's kilometers and kilograms and that kind of stuff. Always use SI units. So ignore the parts in Anderson that tell you that it's very important to know what a slug is. You don't. For next time, tomorrow, we will have a look at the atmosphere, and today was really slow compared to what we will do tomorrow. So gradually we will increase speed and make it more complex. And tomorrow the atmospheric formula will use nearly all the formula that you have on the sheet in front of you. So it would be worth your while to study sections 3.1 to 3.4 to know what's coming at you. Okay, see you tomorrow.
Please visit our OpenCourseWare website for more information. See you at our next